Good evening everyone. In the second discussion of mechanical unit operation course. Now probably you are watching the recorded version of this discussion because currently I am not in India and I am traveling. So hopefully you can understand the situation. So that's why I can't able to go live to now. That's why I recorded the version and one of my colleague is uh, playing on the Google Meet for all of you. So if you have any question at the end, my email ID is there, or else you can ask the question to my colleague also. He can able to answer, or we can take care of the lecture in the next lecture. Okay. So now I want to share my screen. Okay. So this is the second lecture second week discussion. In the second week, the main topic of the discussion is the screening. Last time we discussed with the particle size, shape, density, different characteristics of the particle. Now we have to understand how we can separate the particles by using screening. And after separation, what are the kind of equipment, efficiency, ineffectiveness are applied. Professor already discussed in detail in all the three video lectures. So we will go through some revisit the topics which was discussed by the professor, and then we will do some calculation and understanding how the numericals goes on. Even as you can talk about the assignment is pretty easy for this week, but although will try to cover some more examples which is also discussed by professor. Now there are three lectures is there. One is about screening, another is a size analysis by screening, and the third one is the different equipment, what are the capacity and effectiveness of those equipment. Now this is the outline of our discussion of this today's talk. We will start from the basic of screening, what is the procedure for that, then size analysis from screening. There are two types of size analysis, one for the uniform mixture, another for the non-uniform mixture. Then examples, we will try to solve some basic examples. Then effectiveness of the screen, again example based on effectiveness, and some basic factors, because some assignment questions are based on capacity and factors leading to inefficient separation. So we'll talk all this in detail in today's talk. Now we'll start with the screening. So these are the basic terms you need to focus, or the terms which are come in your mind when you heard about the screening. So you start with the screening, then there are many kind of keywords I can say that are come in your mind. Limiting screening, retaining screen, oversize, undersize, dry screen, wet screen, blinding, actual screen, ideal screen. This kind of fundamental things you need to understand. Then the mechanism, so stratification and separation probability. By screening, we are going to check and use these two kind of properties to screen the materials. Then what are the factors affecting this screening operation? Then which kind of different surfaces are there, like punch, this kind of punch screen. It's not exactly look like that, but I just want to give you some brief intro. Or some, sorry, or you can say punch plates or parallel bars and rods. So then these kind of meshings are there. So many types of, you can say, that screening are there. This is the screen size designation, which it will be in mesh and aperture. We will discuss in this lecture. Professor very well said for this. Then different screens. So there is a Indian, German, South African, US country based screens are there, but most important is Tyler standard. We will follow this standard for the most of the calculation in our lecture. Then method of reporting sieve analysis. Differential analysis can be done and cumulative analysis can be done. Effectiveness, capacity, and how these properties are interrelated with each other, what are the factors affecting this property, and which are the equipment which we are using. So these are the basic terms we can understand when you talk about the screening. Now screening is a separate, what is the definition of screening? Screening is a separating a mixture of various size of particles into two or more portions. So suppose you have some materials which has a coarser particle and as well as some fine materials. If you want to screen them, then you, at the end you will get the fine material and one end and coarse material at another. These are the basic function of screening. Now if we talk about, then so if we talk about the different graph, you can see in this what actually how this screening is looks like. So before screening, the particle size distribution, you can see it's much more like this. It is no, it is very broad in nature, and most of the time it is not that much uniform. So while when we do the screening, it is includes each size of the particle with it. Now when we go for the screening, we will separate them out into a different section. So here you can see, by using this section, the particle size will be much more uniform, particle size distribution which will be much more uniform, and we can easily separate particle based on our requirement. So this is the how mass fraction versus particle size. Mass fraction, that means nothing but the amount of small fraction of the material in order to the particle size distribution. You can see that it is much more uniform and very well distributed after the screening, and it is narrow in nature. Now for screening, as you can say that there may be equipment. It includes moving bars and punch with the metal plate and move on wire mesh, sieves, etc. We all know how sieves looks like actually. So this can be the punch skin either, and some wire mesh and something is like that. It's look like this. And whenever whenever we talk about the screening, so whenever we talk about the screening, then the diameters of the wire and the spacing of wire being is closely specified. We need to specify what are the spacings are there in between these all punches, or in between the all wires. In this distance, it all obviously you can see that whatever the amount of size of material is there, it can pass through it if only and only we specify the distance. The space between the individual wire of the screen is known as the screen aperture. Okay, so for individual wire we have, and the whatever the space we have in between, this is known as the screen aperture. Screen aperture. So as you can see, these are the important phenomena. And generally, if we talk about the screen, then it has a metal pans which has 8 inch of roughly diameter and 2 inches height. Then sides of these are designed such in the bottom of one sieve can be mounted on the top of the next screen. So at the end we will fix the screen on one above each, one above another in the decreasing size manner. So at the end you will get some pen is there, and you will get fine particle, and above all are have the coarse particles. Now mesh number, there is another one important thing, which is one is a screen aperture, another is the mesh number. So mesh number is applied to the number of apertures per linear inch. If we talk about if suppose this is the linear inch of the screen, then for this linear inch, how many number of openings are there? So that is known as a mesh number, and generally screens are available in the market on the basis of mesh number. Now, screen analysis procedure. What is the procedure? Maybe you all go through this procedure, and sir explained very well. Now we just again revisit and understand that why we are using a particular procedure for screening and how it can be helpful for the solving examples. Now, screening is accomplished by passing a crust material to a surface provided with opening of desired sizes. Definitely, what is the screening we already discussed, and set of standard screen. As you can see, all the screens are on the standard size, and they are stick each other on one above the other. So the large mesh size is larger mesh material, like coarse material, which will be in the above side, and as you are going down, the size, aperture size will be reduced, and you will get at the fine material in bottom. Now, so how can we do the what at the end? We will use this kind of take, and we will put the onto the some vibrating mechanical vibrating machine or mechanical vibrating motor kind of assembly, and then at the end we will get some different material on each screen. Then we need to do the analysis. Then analysis can be done in the tabulated form. Now, particles on any one screen are passed by the screen immediately ahead of it. The two numbers are needed to specify. When we talk about this screen material, then we need to talk about the particle size which pass through this screen and which are written on this screen. So these are two things we need to understand. If for suppose an example, this is a 14 and this is a 20, and 40 by 20 means material pass through the 14 mesh screens and it is written on the 20 mesh. Now in the tabulated form we need to specify what is the opening of the screen, what is the mass fraction, what is the average particle diameter in increment. Every minor detail we need to consider, and based on the basis of that we need to find what is the diameter of the overall particle size, what is the surface area of all the particles. Many types of calculation we will perform on the basis of that tabulated form. Now, so how can we represent the screen in the tabulated form? Like what is the oversize which is not passed through the screen, and which is passed through the screen, which is known as the undersize. So if we talk about these three representation, then in the first, as you can see, if our material is written on 3/4 inch mesh or screen size, then we need to just mention that it is on 3/4. In one of the method we need to mention like 3/4 inch, then it is passed through it, then 3/4 inches on 1/2 inch. So it is passed through 3/4 inch and it is on. Now it is on the on half inch screen, it is written over there. So same for 1/2 inch on 1/4 inch. In another, we just have to use the mathematical symbol that if it is on 3/4 inch, then plus 3/4, it is passed in the 3/4 and it is written on 1/2, then minus 3/4 inch plus 1/2 inch. This kind of representation you can use. In the third method, you can use this forward slash. So in the forward slash, as you can say, 3/4 inch slash 1/2 inch. So it is passed through the 3/4 inch and it is written on 1/2 inch. Now maybe types of screening, if you want to discuss, then there may be two types of screening. One is a dry screening, another is a wet screening. In the dry screening, as the word suggests, we are using the screen material which we want to screen without any nature amount of moisture, or nature amount of moisture only, and if it has more amount of moisture, then we need to dry it before the screening. So it is a dry screening. If it is some natural moisture amount of like some 0.1% or 0.5% kind of moisture, then we can use directly. Otherwise, if it has a moisture content some says like 5%, then we need to dry it and then we have to use it. Now in the wet screening, we will use some water So main purpose is sometimes what happen, the material is very much fine. If we go for the dry screen, then most of the material is there are chances to lose the material. So that's why we are using the wet scaling. In that we will add the sufficient amount of water to make it wet, and then we will do the screening operation. Now size analysis by screening. So that's why you always follow this Tyler standard screen series. So we'll follow in all the examples and all the preparation that Tyler standard needs to be followed. Now in the Tyler standards, these are some example how it represents. So this set of screen is based on the opening of the 200 mesh screen, which is established at 0.074 mm. So it is always on the basis of 200 mesh screen. And what is the diameter which is had, aperture size is 0.074 millimeter. The area of the openings in any one screen in the series is exactly twice of the opening in the next smaller screen. So if you have two different Tyler standard screen, then the area of opening of any one will be twice as the another as the next screen, next area of the opening of the next screen. Suppose if you take about the ratio, then dimension any screen that the next. So ratio of, always you need to focus on this, get the ratio of the next dimension of any screen to the next smaller screen in the Tyler screen are √2. It is under √2. It is basically 1.41. So there are many questions even in the assignment questions like that. In the Tyler screen, the ratio of the mesh dimension are in which value? It is always in the √2. If we talk that in between two screen, if some intermediate screen is also available, then that intermediate screen has a mesh dimension of 4√2 or 1.189 times that of the next smaller standard screen. But generally we are not in the operations we are not following these intermediate screens. So if any high experiment analysis only require this calculation, but generally you need to focus that the dimension ratio of the Tyler screen like consecutive dimension, consecutive order, it is always into √2. And this is how the representations look like: mesh number, then the clear opening inches, then clear opening in millimeter, then approximate openings in inches, and wire diameter in inches. So these are professor discuss all the mesh number, so you can directly correlate it. If it is mentioned that mesh number 4 is there, so what is the opening of the in inches and millimeter, and what is the wire diameter for it. Okay, now size analysis of uniform mixture. There are two types of, now we will discuss the equations. There are two types of mixture. One is the size analysis of uniform mixture. So if our mixture is a uniform which has the same amount of diameter, particle diameter dp, and the volume is Vp, which we can consider that Vp is equal to m by rho p, as rho p is equal to m by Vp. So if we don't have volume, then we can have, if we have mass and density, then we can consider m by rho p is the particle volume. And the particle shape, we in the last lecture we discussed about the sphericity. That sphericity is equal to phi s is always 6 Vp by Sp into dP. This is the formula. If we know the particle shape, and if we don't know, then also if we want to represent it, we always need to represent with the help of sphericity. And this is the diameter, volume, and sphericity. So we need to calculate the number of particles in the sample in order to do the size analysis. The number of particles is definitely is equal to m by rho p into Vp. Vp is the volume of one particle. We need to find the total number of particles, one particle volume, and we have to give one Susan this is nothing but the total volume divided by one particle volume. So if we suppose to have 1000 centimeter cube total volume, and we have 10 centimeter cube one particle. The number of particles is equal to 100 numbers of particles available in sample. So total volume this represent in the form of mass and density. Then from this total number of particles, if we multiply it with the total surface area of one particle, then total number of particles in the surface area of one particle is represented the total surface area of the sample. So this is how we will do the size analysis for uniform mixture, and we need to always keep in mind this equation that n into Sp is equal to 6m divided by 5s Rp into dP. Now diameters for this screen size analysis, particle size analysis, diameters are based on various applications. So you need to understand which kind of diameter is followed, and we will discuss in the later part of the talk. But now we will do one example on the basis of the discussion which we just see. The example is like, what is the total surface area in meter square of uniform particular sample consisting of hemisphere of diameter of 1.125 millimeter each. So hemisphere, we need to consider the shape is a hemisphere, and particle diameter is 1.125 millimeter. So it is a uniform mixture. Then density is equal to 2150 kg per meter cube, and sample mass is 75 kg. So now if we these are some given data. If you want to find the volume of the total sample, then m by rho p comes around 0.03488 meter cube. All other things are given. Now in order to find the particle, in order to find the surface area, we have to just start from the volume of one particle. So for the one particle, if we talk about the hemisphere, so as we know that last lecture we discussed that hemisphere will be represented by pi d cube by 12. So it is if you use the convert 1.125 millimeter into the meter and you substitute into this equation, at the end you will get 3.106 into 10 to power minus 11 meter cube. This is the volume of one particle only. But now we need to consider how many number of particles are there. So for total number of particles, we need to just do the simple calculation of total volume divided volume of one particle. We need to do the same thing, and if you do that, at the end you will get the number of particles. It is like 9 crore 35 lakh 40,000, some around like that. And after that we need to find the surface area. For the surface area of single particle, before that we need to find the surface area of a single particle, and then we can do the calculation n into Sp, where single particle surface area will be multiplied with the total number of particles, and then we will get the total surface area. So single surface area for single particle is 3 by 4 pi d square. For the hemispheres the shape, you always consider keep in mind which shapes we are discussing about. So it comes around 2.98 into 10 to power minus 6 meter square. Now go to total surface area n into Sp, and at the end we will get 278.9 meter square, which is the total surface area of our whole uniform particle sample size. Now another method for doing the same calculation is also represented. You can use any method. So for this hemisphere, we all know we need to find the nominal diameter or equivalent diameter. So for that, this pi d cube by 12 hemisphere volume is compared with sphere volume, and we will find that dP is equal to 0.794 d. This already we discussed last lecture, and in the professor discussion in the first week, and we also solved some example on the basis of hemisphere and different shapes. Now even we know the phi s also we calculated, and you know how to calculate it. Is now 6 Vp by SPdP. If you use that equation, at the end you will get 0.840 for this particular shape. And if you use this equation A equal to 6m divided by 5s rho p into dP, then also you will get total surface area is around 278.94. So it is approximately same with same of that another method which we follow. Now this is how you can solve the example for the uniform particle size mixture. Now if we talk about the size analysis of non-uniform mixture, then how we will follow. For the non-uniform mixture, like it has different size of materials in it. So for uh, this kind of size analysis, we have to follow the methods general method, which is one is known as a differential or fractional analysis method, another is known as a cumulative analysis method. So we will see the difference. And in the differential analysis, sample of particle having the various size sizes and densities mixture is divided into the fractions. We divided each fractions into the which different size and densities into the different fraction. Then each fraction has a constant density and approximately constant size. Then we can follow it, consider it as a uniform mixture, and we can do the calculation. But there are many number of methods which we can follow after that. If we talk about the cumulative analysis, then obtained by the consecutively adding individual increments starting with the containing the smallest particle and plotting cumulative sums against the maximum particle diameter in the increment. Okay, so you need to always add all the increments starting from the smallest to the largest. Now this all theory was already taught by professor in the lectures. I am just going to revisit. I am not going to much detail into that, but we will see the examples on the basis of that, and we are directly related this theoretical part with our application by in the base of examples. So that is our main motto. So you don't consider that I will go for each and every minute detail. Professor is explained very well. So for that it can also be made on semi-log and log probability operator. So in that we need to add each and every section by in the cumulative manner, and here we consider the fractional analysis. So in the fractional distribution you can see this kind of chart you will get on mass fraction versus average particle size charge is like this. But we are doing the cumulative analysis, then there are two types of cumulative analysis: cumulative fraction smaller than your particular diameter which you are talking, particle size diameter, and cumulative fraction larger than the particular size diameter. So according to whatever your assumption, you will get either this kind of curve or this kind of curve. We will do the practical example in the next few slides. Now as discussed in this particular second week lectures, that many kind of different specific surface area and diameter of particle has different kind of formulas are there. So when we talk about the uniform mixture, we don't need to go for different values of the diameter and different values of the density, but density must be same, but difference value of the diameter and difference value of the mass fractions. So but when we are go for this such big cumulative and fractional analysis, we need to always consider that every different size of material, like here it's small material, fine particle, here big particle. So every different size of material has a different diameters as well as different mass fraction that is returning on the screen. So you need to consider individual each and every mass fraction and on every screen, and with their average particle diameter. Average particle diameter is nothing, it is an average for the smallest and largest particle diameters in respective increment. Every increment, if you want to go for the average, then you need to just take the average of smallest and largest particle diameter, which we will follow and so in the example. Now I am just listing out some formulas which are discussed in this session. That one is uniform mixture, we follow A equal to total surface area equal to number of particle into in single particles number of particle into single particle surface area. But if we talk about the various increment and various non-uniform sizes, then you need to consider it as a I, and you just need to add one by one. for all the different sections, right? Then you will get the equations like this: 6 by 5s rho p summation I equal to 1 to n xi by d bar p. And now if we talk about the average particle sizes on the basis of volume, surface, mean diameter, this is a one way to find a specific surface area. When we are talk about the average particle size, then volume mean diameter is the another way to use the diameter, calculate the diameter. And I am not deriving any of the equations in this session. You just have to note down, and there are many different kinds of diameter which we follow. But volume surface mean diameter is always generally used in many kind of calculations. So we will follow this volume surface mean diameter, and it is also known as a shorter mean diameter. So d bar s equal to 6 by 5s AW rho p. And at the end, if you derive this equation, it is easily represented by d bar s equal to 1 upon summation I equal to 1 to n in bracket xi by dpi bar. Now, if number of particles in each fraction Ni is known instead of mass fraction, if we know before that we do the mass fraction, that Mi divided by m, which is represented by xi. Now if we don't know the mass fraction and if we know the numbers Ni, then this is the equation which we can follow. When d bar s, at the end you get Ni d bar pi I d bar pi cube divided by summation I equal to 1 Ni d bar pi square. So here we consider the b in between the derivation of this equation, which is the area step factor. But at the end, in the final equation, you can't find any p. So if you have number, then you can use this equation. D bar s is also known as the shorter mean diameter. So it's the same d bar s. If you have the xi, then the another equation can be used, and if you know the Ni, then this equation you can use. And it is known as a shorter mean diameter, and it is very useful in many of the practical application and many of the examples also. Okay, so here just don't follow this. Okay, now arithmetic mean diameter. For the arithmetic mean diameter, d bar n is equal to summation I equal to 1 to n Ni d bar pi upon nw. Mass mean diameter, the same thing. If you, this is the whole derivation, you don't need to follow this. At the end, this is the equation: d bar w is equal to summation I equal to 1 to n xi into d bar pi. So xi is the mass fraction in which is in the multiplication of average diameter. So you need to just add all the mass fraction with their diameters, and then you will get the mass mean diameter. There is a volume that was before that volume mean diameter. This is mass mean diameter. Now we also volume to surface mean diameter. This is a volume mean diameter. In the volume mean diameter, the equation is d bar v is equal to 1 upon summation over xi by d bar pi cube whole raised to 1 by 3. You can say under cube root of, you have to do the calculation of summation xi by d bar pi cube. So in its number of particles, if you want to measure, then you need to use this Ni is equal to mi upon rho p into Vp. Total particles is mi upon rho p into Vp for summation I equal to 1 to. Now we will discuss the examples which we are following by using the equations which we did, which have shown. Now you have to understand that why we follow different types of diameters, and according to our application we follow one of it. In your examples, generally in this assignment for this second week, examples are very easy, but we need to understand for the complications of the example. That is not there, but if we follow the equations and if we do the calculation like this, it will be useful in your examination. That's why we are following the whole details of detailed example here. So in this, as you can see, the mixture of solid consists of 10% of spherical, 20% of hemispherical, 30% of cylindrical, and 40% of cubical particle. There are 4 different types of shapes will be there in this mixture of solid. The density of the sample is total density is 2650 kilogram per meter cube, and the diameter of the spherical particle is 2 millimeter, and the diameter and height of the cylindrical particle is 2 mm each. So here the equal height and diameter cylinders are used. The diameter of hemisphere is 0.5 mm, the size of the cube 0.1 mm. So these are the 4 types of different shapes available, which is the percentage of their shapes, and these are the all diameter details for size details for their all those shapes. Now calculate the sphericity of the each particle type and obtain the specific surface of the sample. So this kind of problem professor is also discussed. So please go through all the problems for a better understanding of the concepts. In assignments, maybe the problems are not there, but you need to understand how these problems can be taken care of. Now we have 4 different size: sphere, cylinders, hemisphere, cube, and all the particle size are given. Then for mass fractions are also given. Now they ask to find the sphericity of each and every particle. So we already did this calculation in our last session. So we know that how can we use the equation of 6Vp divided by Sp into dP in order to find sphericity. So you can find the sphericity for individual particles. All other details are given. You can find the diameters, nominal diameter, and then you need to find this specific surface area for this equation, for this problem. So in order to find the surface area, specific surface area, we saw the equation. The equation is like this: AW is equal to AW is equal to 6 rho P summation of xi by pi si dpi. So if you follow the equation and if you just do the calculation here, xi by phi si dpi, you already calculate all these things. So at the end you will get the total surface area, which is 10,867 something. So this is the solved example in the professor's lecture. We just go through and understand how it is it has been done. Now we will see the product size. This is another example. Product size distribution of a sample obtained by screen analysis is reported below. So there are different mass numbers are available, screen openings and mass fractions given. So according to this, you can see that these are the mass numbers ranging from 8 to 200, and mass fraction on each and every mass is provided. Now what you need to find first is a draw undersize and oversize cumulative analysis. As we discussed that whatever material which is passed through the screen, it is known as undersize, and what is written on the screen, it is known as oversize. So you need to draw the analysis and then calculate specific surface of the sample and total number of particles. And the third thing you need to find that obtain the volume, surface mean, mass mean and volume mean diameters of the sample. You need to find the outer diameter, mass mean diameter and volume mean diameter, all this diameter for the particular one example. So that's why this example I deliberately choose, although professor discussed that it includes each and every kind of diameter in it, so you can understand how to do the calculation. Then data for the mixtures are given, shape factor, sphericity and density are given. Now we start from the undersize and oversize cumulative analysis. So for that, these are the things which is given in the problem: different mass number, opening size and mass fraction. Then average diameter is this. So if we talk about the cumulative undersize and cumulative oversize, how can we find? So for the cumulative undersize, if we talk, then undersize it is that if we talk about the mass number 8, then if we talk about the first mass, then undersize means whatever the material passed through that mass number. So here you need to do the addition of all the mass number which is below the first mass. So if you add all this thing, and at the end you will get 1. So that's why you can say that cumulative undersize for the first mesh is 1. Then what, while you thinking about the oversize, how much material is written on this first mesh, and you can directly say that all the mass fraction is given after this first mesh. The first mesh nothing is written, it is given in the problem. So that's why we can use that 0. And then if you talk about the second mesh, in the second mesh you have to do the calculation for all the material that was passed through for the cumulative undersize. So total 1 and minus, or you can do the otherwise, that 1 minus, you remove the whatever material which is written on that mesh, and then you will get the cumulative undersize. But if you talk about the cumulative oversize, then cumulative oversize for this particular mesh is given to for this particular mesh, you can see nothing is there above this mesh, so that's why it is 0. But if we talk about this 1.16 set, then so you can see that mesh number 14, 10 much, what is this is mass fraction is the already material which is passed through it. So at the end you will, like this, you will do the calculation for all this 14, 20, and you will, if you suppose you will want to calculate for this 20 mesh number, so, and if you go for the undersize, then you need to do the undersize up to 0.2 plus 0.2, 0.4, 0.09, 0.06, kind of all these things, and then you will get 0.38. If you want to do the oversize, and for the oversize you need to do the calculation of 14, 0.03 and 0.025, and then you will get 0.17, which is the cumulative oversize. So now there's time you will see one decreasing pattern for the cumulative undersize and one increasing pattern for the cumulative oversize. So in the first our calculation will be completed if you just plot this cumulative oversize and undersize value. As you can see, it will be passed through in between somewhere near 0.5. So it is not exactly, but exactly if you do the perfect calculation and do everything, the both will be mass fraction versus particle diameter. In that cumulative, this is both the graph will be meet at, so this is oversize and this is undersize. It will they are meet at particular 0.5 mass fraction only, 50%. Now for the different diameter calculation, we need to calculate xi by dpi, xi by dpi cube, because these are all things are there in the equations. So that's why when we are found tables, in the table we need to add some columns like xi by dpi bar, xi by dpi bar cube, and xi into dpi. Xi into dpi for the mass mean diameter, this is for volume mean. So this is the volume surface mean diameter, and if we add them at the end, so addition will be provided in the equation, and at the end you will get the answer. So for the same reason, all the mass fraction with a particular diameter are chosen, and we already performed the different calculation like xi by dpi, xi by dpi cube, and xi into dpi, and you will already have this summation. Now this can be used for different questions which was asked in this problem, that specific surface and number of particles need to be calculated. Then AW is equal to 6 by 5s rho p, summation I equal to 1 xi by dpi. So we already have all this summation from our table. If we just multiply it with our 6 by 5s into rho p value, then we will get this 5551.03 millimeter square per gram. This is specific surface area, and number of particles is xi by dpi cube. So and if we multiply it with a1 upon a into rho p, then we will get this 71246.2 particles per gram. This is a is equal to surface, what you can say, this is a constant which we are using for the whenever calculate the space particles on the basis of surface area. So this is a constant based on the surface area. Now everything will be given in the equation. Now we know that at the end of our whole screening, the end is the pen. So we need to whatever the fraction which we are written on the pen, we need to subtract it in order to get the actual specific surface area number particle. So for that, for this subtracting prime fraction, we divide AW and NW by 1 minus 0.005, which is the fraction which was written in the pen. So at the end we will get the exact value of AW and NW. Now average particle diameter was asked in the same example. So different kind of diameters were asked. Volume surface mean diameter, volume mean diameter, and mass mean diameter. For this we have the summation of xi by dpi, xi by dpi whole cube, and xi into dpi. Just all this summation we have to put in a particular manner in every equation, and at the end we will get the different kind of diameters. Now why there are many diameters, as already discussed, depending on your application you will use only one kind of diameter, and you can see there is a very large deviation or very large difference in every kind of diameter. So that's why according to your designing of the mechanical operation, or according to your particular application, based only you need to consider any of one diameter and process with the calculation. Now effectiveness of the screen. So screen, we always say that whenever we are using the screening operation, then effectiveness of the screen will be varied on the basis of, sometimes if there will be you can see that screen is there and screen has some rupture in between or something, then effectiveness will be lower down. If you perfectly separate out all the oversized and undersized material, then we can say the effectiveness of the screen will be much higher. Like this, there are several ways to understand how this effectiveness of the screen will be vary and what are the different values. So maybe there are mainly three methods which we are going to discuss, and how can we use all of these three methods to understand what is the effectiveness of our screen. So in the first method we will use both the rejection material, like undersized material and oversized material. So recovery in the product of desired material in the feed. So whatever the recovered material which is there in the feed, and the another is rejection from the product of the undesired material. So suppose oversized is your desired material and undersized is undesired material. So both you consider amount, and then from that you find the effectiveness of the screen. In this we consider the mass fraction of desired material in the product, in the feed, and in the reject. Everywhere whatever the desired material, whether it is oversized, undersized, we need to consider, and mass fraction of every in the every different section of that particular material we need to consider. Then P, F and R, total mass of product, feed and reject, that we need to consider. And we use these equations like for the recovery, what are material that recover. So that's why we can say that okay, our product fraction which can be divided from the feed fraction for the desired material, that can give our recovery. If you talk about the rejection, then 1 minus this whole equation, you can do calculation and you can get that, because anyway this is the simple mass balance. So total mass fraction is always 1. So if you want to find about the rejection, so whatever you recover, 1 minus recover is known as a rejection. Then effectiveness is the recovery and rejection. So if you use this equation, you will find the effectiveness of the screen. But for this operation you need to find whatever the weight of your feed and product every time. But in the continuous process your product weight is not always there. If you can able to estimate your feed weight, but product is always in the continuous manner. So in that kind of scenario this equation can't be used. And how to decide whether oversized material is product or rejection. So whenever we are discuss about the oversized material in the continuous process, then it is very difficult for us if it is product or rejection. By using this kind of effectiveness formula, it is difficult to understand. That's why there is some another methods. In the second method we will do the mass balance. That since weighing of entire feed and product is not practical in continuous process, so we will use the another equation where we will do the mass fraction, F is equal to P plus R, and we will put the different fractions with it. So this is the overall mass balance, and if we go for the component, then or fractional mass balance, then xf into f is equal to xp into p plus xr into Now according to what you need, P by F or anything like if you want to go for a product or you want to go rejection, on the basis of that you need to do this ratio. As you have the mass fractions always, so you can do this ratio, and for the recovery the same equation you have to use, and for the rejection the same equation, but here you don't need to consider your mass of the feed, product or rejection. You just need to have the mass fraction, and from that mass fraction you can use the equation for the calculation of effectiveness. This is the recovery, rejection, and if you multiply both with each other, at the end you will get one equation which can give you the value of effectiveness. And there is one third method also. In this third method, it is based on the product of recovery and enrichment, which gives the effectiveness. It's the same kind of equation. We will just focus on the product of recovery, and xf minus xr, xp minus xr, xpx. So these are all being taught in the lectures. Now we'll see the example on the basis of this. Now data on screening operation is presented in the table. So everywhere in this screening practical size screening examples and operations, you always find the tables, because there are many screens are there, many fractions are there. So from the table you need to calculate the effectiveness, whether you want to calculate effectiveness, whether you want to calculate diameters, everything. First the table, you need to simplify the table in order to do the calculation. The screen used for the separation has an aperture size of 460 micrometer and 100 kg over of feed. A process obtain 650 kg overflow. Calculate the efficiency of the operation. So this is the feed and overflow are given. So we need to find the efficiency. Now, so this is the table. In the cumulative fraction is already given what is in the feed, what is in the cost, and what is in the pass. Fine. Now for the finding the efficiency, as you can see, feed, cost, and fine, every material has every kind of fraction is there in every material, every feed, overflow, and underflow. So this is not an ideal case that every fine material is on the fine cumulative fraction, fine sizes, aperture sizes, and coarse material is only on the coarse. Everything, everywhere, mixing of all these fine and coarse materials are there. So for that, from the mass balance, if you want to find that what is your exact product size and what is your diameter, so you have to do the cumulative analysis to get fraction for cut of the diameter. So as you don't know the exactly which diameter is there, which is given for after that you can consider the oversize, undersize. So for that you have to just plot the cumulative mass fractions versus aperture opening, and then here 460 micrometer is given. The 460 micrometer aperture size is not there. So what is the fraction at the 460 micrometer? It is given from this plot. And from this plot you will get, this is the for the fine with undersized material, or you can say product on the basis of your application, or rejection maybe. So rejection is 0.14. Then feed, and feed it is around 0.58, and mass fraction is on product is around 0.85. So coarse material is your product. So at the end you will get all these different mass fraction. Now you have to do the same utilize some equation in order to find the effectiveness of the screen. So here all the, as we know, the P and R for all the this mixture, so we can use all the effectiveness equations, and you can see according to the different methods you will get the effectiveness of the screen differently. So that is why same like the diameter, on the basis of your application you need to use the effectiveness formula, and then you will get the effectiveness according to your application. So that's why you don't have to rely on any one effectiveness. You need to go to check others also, and you need to find that what is the suitable for your operation. So basic, that's why I don't want to go into much detail. You just have to substitute the values. Now capacity of the screens. In that we will say what are the factors which will be reduce the capacity of the screen, or capacity of the screen will be dependent on which kind of factors. One is a rapid feeding. If you feed rapidly, very, like this is the screen, you just consider, if you feed the material very in the fast manner, then there might be a chances that your undersized material, its product can be go here. If it will, must be, your product is undersized and it needs to be go here, but some part of product or major part of product can be go into the screens, and maybe blocking and everything can be happen if you go for the very rapid rate. And two strip angle of the screen, sometimes this is a strip way, it should be at particular angle, but if you use the lower angle, then there might be chances to reduce the capacity of the screen. Then insufficient time for the complete separation, you need to provide the sufficient amount of time in order to separate the coarse and fine particles. If you are not providing, then also it will be a problem for the skin capacity. Excessive dampness in the feed may cause cohesion of small particles to form large masses. So dampness, if it have moisture and everything thing is there, it can cause the cohesion of small particle and it will be agglomerate into the large particle, or sometimes addition of small particle into large particle, that will reduce the block the apertures and it will reduce the capacity. Now sometimes your skin is worn and then you also create a problem. Sometimes your screen will be blind because of some undersized material or oversized material. Undersized material go into the oversized material and it is blinded. So that's why many reasons are there. So that kind of reason must be, in order to determine your capacity, you need to focus on this kind of factors. Now for efficient separation, which are the different factors which we have to understand? So these are, I just want to just listed out because some of your assignment exam questions are based on this kind of theoretical explanation. That's why I just want to give you that explanation again, and from that you can take your call on giving the answer of that particular question. So capacity of skin and effectiveness are closely related. You need to understand capacity is always much related to the effectiveness. If the capacity is more or less, then directly affect the effectiveness of the operation. So if a low efficiency or effectiveness may be tolerated, then skin may be operated high capacity. If you have a very high capacity operation and you are overflowing your materials in order to using your screen, then there are many chances, major chances for getting low efficiency or effectiveness. Then ability to of the device to prevent blinding of the screen surface is probably the most important factor determining the capacity of the screen. Many of time device of ability of the device which can prevent the blinding of the screen surface probability the most important. Sometimes we are using some device which can prevent the blinding of the skin, and that is its ability to do work is most important while determining the capacity. In the dry screen, the greater the amount of moisture or dampness in any particular material, the lower the capacity. We already discussed in the capacity part. Because of the greater surface area, finer material can tolerate a greater percentage of moisture. So as you can see, fine material has a very great surface area. We all know that that's why it can tolerate a great amount of moisture. So we need to always keep all these factors in our mind in order to not leading towards the inefficient separation. We have to always go and do the efficient manner, separation in the efficient manner. So you will sometimes you will get this click and other marks in your presentation. Just please neglect all this. Now the books and references mentioned from the professor, and we follow for the example. So McCabe Smith, Ortica Rivers, most of the examples are on basis of all these standard books on chemical engineering. Now at the end, I just want to give you one thought, and as with my mail ID, that one of the this thought was given from our time our ex-president and very noble person Dr. APJ Abdul Kalam, one of the very important characteristics of a student is to question. You always needs to ask questions. So as you can see, it's in this recording version. We will not much discuss with each other, and there might be some lag with that. But you always go through this presentation with video lectures, and please ask the questions to yourself, and you can convey these questions to our team and with us. We will definitely solve your answers, and we want to give you the answer for those questions. Thank you very much for attending the lectures. If you have any question, please drop into the chat box. I am trying to cover it in the next session. Next session maybe again in the recorded version, but after that I will again come into India, and then we will again do all the live sessions, hopefully very well. Take care of yourself. Bye.